In this video, we are going to discuss three properties of Riemann integration as consequences of Lebesgue's criterion for Riemann integration, which we looked at previously. The context here is imagine that we have a nice bounded domain A, and f is a bounded function which is Riemann integrable on A. So our first property says that from f, you get another Riemann integrable function formed by taking the absolute value of f. So that's something that we have to establish. The absolute value of f is a new function, which we will show is Riemann integrable in its own right. And also we have this relationship between the absolute value of the original integral of f over a and the integral of the absolute value of f over a. Then our second property says that, if a has measure 0, the integral of f over a is 0. And I would like for you to imagine that as like a generalization of this familiar statement from calculus. So the integral over a single point of a function is 0. That's something that you probably know very well. This is kind of like broadening this statement. So integrating over a point, we can now think about integrating over a measure 0 set. And then the third statement is that if you have a non-negative function, so any area it encloses can't cancel itself out with negative area. That's why we insist here that f is non-negative. Were you to integrate that function over a and discover that its integral is 0, then that means that the set of points over a where the function is non-zero has to be a measure 0 set. There's an expression that we can use here. We can say f of x equals 0 almost everywhere. So AE, abbreviated like this, means almost everywhere in math. And what you can think of this as, in this context, f is 0 except on a measure 0 set. We're going to use Lebesgue's criterion to prove that the absolute value of f is also a Riemann integrable function. The context here is that we have a nice bounded domain A. So when we think about reasons why the absolute value of f would fail to be Riemann integrable on A, referring back to Riemann's criterion, we recognize that would happen if its set of discontinuities did not have measure 0. We will work this all out in detail, so I'm just kind of saying it out loud right now, but we are going to show that the absolute value of f on any rectangle enclosing A has an extension whose set of discontinuities has measure 0. Okay, that was a lot of words, so let me now start to translate it into mathematical ideas in writing. Let's first take A and enclose it in the usual way in a rectangle called S. So let S containing A be a nice rectangle in Rn. I'm using the word nice here almost in a technical way. We've done this so many times. So when I say nice rectangle, I mean an n-dimensional rectangle whose sides are parallel to the coordinate axes. Define with f tilde the extension of the original function f to s. So let f tilde for any x in Rn really be f of x if the input x is on the original domain A, or rather from the original domain A, 0 otherwise. So that's the extension of f to the rectangle S as we've seen it before. Notice if I take the absolute value of this function, then by the way that we defined it, that would be the absolute value of f of x if x is in A, and the absolute value of 0 otherwise. And this is exactly how we need to extend the absolute value of f. So here it's like a composition of operations. So first extend f, then take its absolute value. Now we want to reverse that. Take the absolute value of f and then extend that. I'm just trying to think. I want to have the x here. So let's do absolute value of f at x. Extend that. I think that's the notation that I want here. So the absolute value of the extension is the extension of the absolute value. That's a very nice, clean statement. Hopefully you were anticipating that. To show that the absolute value of f is Riemann integrable on A, I need to understand the set of discontinuities for this extension. So we want to prove that the set of points where this extended absolute value of f is discontinuous is a set of measures 0. To do that, we are going to show that the set of discontinuities for this function is a subset of the set of discontinuities for this function, which is the extension of the original function f. Let me write that down as our goal. I'll put it in orange, and then we will get there through the contrapositive, I believe. So that's going to be the natural approach. So we want to show the set of discontinuities. Let me write D for the extension of the absolute value of f. So the set of discontinuities for this function is a subset of the set of discontinuities for this function, which has measure 0 because the original function f satisfies Lebesgue's criterion for Riemann integrability. Okay. This is a set containment proof as it's written right now. So I could say, take some point in the left-hand side, show it belongs to the right-hand side. That would be a direct proof. I'm going to actually proceed indirectly. Let me prove instead that if the original extension is continuous at a point, so is this one. If you don't see that's immediately a contrapositive, we will readdress that in just a moment, but let me put the argument down. Suppose that the extension of f is continuous at some point P in Rn. Then there's a sequence, for every sequence of inputs which converges to P, we can apply the sequential criterion for continuity. So if xn, let me do xk, xk converges to P by the sequential characterization of continuity, plugging this into f tilde converges to f tilde of P. Okay. But by algebraic limit laws, I mean, this is a sequence of real numbers because these are scalar value functions. I can just take the absolute value of both sides, and in the interest of space, let me just kind of add absolute value bars right here, like that. Take a moment now to see if you can finish the argument to show that this function is also continuous at P. So that's where I would like for you to get to next. I'm sorry, I didn't leave you with a very big exercise to do because actually it follows immediately from this. So if you wanted to take it further, you were welcome to. We just showed that this expression can now be rewritten as the extension of the absolute value of f of this sequence. So this function evaluating the sequence xk converges to this function we're trying to understand. So the extension of the absolute value of f of P. And then we just write that that implies, switch markers, that this function is continuous at P. Again, with the sequential characterization of continuity. Starting with the hypothesis and going to the conclusion, if the extension of the original function is continuous at P, then the extension of the absolute value function is also continuous at P. Let's now pass to the contrapositive. If the extension of the absolute value of f is not continuous at P, I think I can fit it on here, not continuous at P. The original extension is not continuous at P either. Let me have you digest this for just a moment. I claim we're basically done, but see if you can connect this back to what we wanted to show for just a minute. We have now shown the set containment that we wanted to show. If P is a point where the extension of the absolute value of f is discontinuous, that means the hypothesis here for this contrapositive statement holds at P, then the extension of the original function f is not continuous at P either. So D, the set of points where the extension of the absolute value of f is discontinuous is a subset of the set of points where the original extension was discontinuous. This, I'm going to say the rest out loud because I'm struggling to speak and write at the same time. This is a set of measure 0. We have proved already that any subset of a measure 0 set has measure 0 in its own right. So now the set of points where the extension of the absolute value of f is discontinuous is a set of measure 0. Lebesgue's criterion for Riemann integrability is satisfied. The absolute value of f is also Riemann integrable. I really filled up the board, but it's not a very large argument. So let me have you read through this for just a moment. And we have actually another result to show because this is really 2 statements. We will also quickly establish this inequality before moving on. For the inequality that we need to show now, let me just do this algebraically with no words. On A, we know that negative absolute value of f is less than or equal to f is less than or equal to the absolute value of f. So that's always true. We proved previously that Riemann integration preserves monotonicity, meaning that I can now drop integrals here, and we preserve this inequality. We also proved that the Riemann integral has linearity, and that's important here because I need to pull this -1 in front, but we're welcome to do that through the linearity property. So let me write this like this. And now we actually have exactly what we need. I can get it all down. Because I have the same quantity on the right and left, but with a negative sign, whenever you have this kind of pair of inequalities, so you have this chain of 3 terms being compared here, where you have exactly the right-hand side and the left-hand side in this format, that means that the absolute value of the middle term is less than or equal to the absolute value of this term. So I can write the absolute value of the integral over a of f is less than or equal to the absolute value of this, which I will write, although it's not necessary, because we know that if this is greater than or equal to 0, so is the integral of that over a. So let me just make that replacement. Like so. That's exactly what we wanted to show. This is a result that's easy to quickly remind yourself of if you're ever like, oh, am I getting it turned around? Just sketch a function of one variable. Say I have this function as my original f, maybe going out to 5. Okay, so if I wanted to compute the integral of this function f, so let me say, okay, lots of markers. This is the function f, and I do the integral of f from 0 to 5. What am I going to be computing? It is this positive area plus this positive area, but minus the area that's down in the 4th quadrant because we have signed area in this computation. However, when I take the absolute value of f, all that's negative gets flipped to be, if anything, positive. So of course, the integral of the absolute value of f is only going to enclose, if anything, positive area under the curve. That must be greater than or equal to the original signed area once you've taken its absolute value. Okay, so everything that was negative turns positive. So you can rederive this on the spot, again, if you ever are wondering if you're writing that down incorrectly. Again, the second statement is kind of like generalizing the idea that integrating over a point is 0. Here we're going to prove that integrating over a measure 0 set is 0. And we're going to use the result that we just proved. So there was a reason why we did that first. From prior result, by the result we just showed, we know that the absolute value of this function is also Riemann integrable. So I kind of removed the hypotheses here that we had on the first slide, but the context was A was a nice bounded subset of Rn, and F was bounded and integrable on A. So the absolute value of F is also integrable, and the integral over A of F, omitting differentials just to save room, is less than or equal to the integral over A of the absolute value of F. So if I could prove that this was 0 instead, then I could know that this was 0, and so what's inside is 0, and that's what we want to get to. Let me just write that as a want to show. And I think that this is an easier approach than sticking with the original function, because what's nice about the absolute value of f is I know that all of its values are either 0 or positive. So I don't have to worry about, cancellation or anything like that. I can really just think about having a non-negative function here. Take a moment. Let me give you a little assignment. Sketch a domain in R2, enclose it in a nice rectangle, do a partition, and think about what any subrectangle of a partition of a nice rectangle enclosing a measure 0 set could contain from that set. Okay, I'm being kind of strange with my instructions, but basically, if we were to enclose this measure 0 set in a nice rectangle and make a partition of it, what could that rectangle contain from the original set? Okay, so there's a rectangle, and we will address this together in just a moment. What I'm about to say isn't a result that we showed directly, but I think that you will believe it. It's something that we could prove on the side, but I don't want to do it in this video to get sidetracked. The idea here is that if this is a subrectangle formed by a partition of some nice rectangle S enclosing the domain A, then this rectangle cannot be entirely contained inside of the domain A. So, A might intersect with this rectangle. We might have non-empty intersection between A and this rectangle. So here, A is like a curve on this board. But there must be a point in this rectangle which does not belong to A. So, say this point out here is not an A. And again, I don't think I've proven exactly this statement before, but the idea here is that if this rectangle entirely belonged to the set A, this rectangle has a positive volume. In fact, it has a positive measure, which means that the set A would not have measure 0. So what we are about to write down in words is that if we take A and close it in a nice rectangle and then create any kind of partition of it, every subrectangle created by that partition must contain a point from A complement. Okay, let me erase this, and then I will start to write that down. Give me just a second. Let's write that down now. Let S enclosing A be a nice rectangle in the usual way. We'll just do that. Let P be any partition of S into subrectangles. Let me name these subrectangles S sub I. And it's always a finite collection when you have a partition. Notice that since A has measure 0, no subrectangle can be contained inside of A. And again, I'm kind of using a result there that we haven't talked about because we haven't really talked about positive measure, but the idea here is that all of these subrectangles, they have a positive measure, and so they can't be a subset of a measure 0 set. So for all I, since A has measure 0. That means that every such subrectangle contains a point from A complement. Okay, what I would like for you to do now is take this partition that we have, only the information we have, and write down the lower sum of F with respect to this partition. Take it as far as you can. To be really correct, as we finish this argument, I think what we should do is take this absolute value function and formally extend it to S in the usual way by setting it to be 0 outside of A. I'll do the little tilde symbol to mean that we've extended it. So basically, it's F when the function is over A, 0 otherwise. Okay, what are we about to do? We're going to do the lower sum. Let me point out first that since no subrectangle is contained inside of A, every subrectangle contains a point from a complement where the extended function is set to be 0. Let me write that down, and then we will do the lower sum. Thus, for all I, there exists some input from the ith subrectangle such that if I take the absolute value function and extend it to that value x, it would be 0. So this means X is in a complement. Okay. Since it's a little strange here, but I mean, every subrectangle contains a point from a complement where this extension will be 0. Okay, so let's do the lower sum of this extended function with respect to this partition. Consequently, the lower sum of the extended function with respect to this partition is the sum over the capital N subrectangles that we have made of the infimum of the extended function times the volume of that ith subrectangle. Here's what's nice about working with the absolute value function. I know that the function takes 0 on each subrectangle, and it can't go below that because we have absolute values. So again, that's nicer than working with the original function where we could have had positive and negative numbers. I know for a fact at this point that every single subrectangle contains a place where this non-negative function is 0, and therefore what we're looking at here is adding up 0 with itself, capital N times. And that's great because we already know that this function is Riemann integrable, which means it's equal to its lower integral, which is the sup of all lower sums. All lower sums are 0. Let me finish that here. Thus, the integral over a of the absolute value of f, we already have Riemann integrability for it, so I know it's equal to its lower integral, which is equal to the sup of all lower sums. Lower sums meaning lower sums of the extended function. But that's the sup of the single element set 0, which is literally 0. And I will stop this here because we've now proved that this integral is 0. Therefore, the absolute value of the integral we wanted to understand is less than or equal to 0, so it equals 0. So what we're taking the absolute value of is 0. Let me just write that. Thus, the integral of f over a is 0. Okay, now I should draw the box. And that wraps up the second statement. Again, where I think it was nice to pass to the absolute value function. We will wrap up this video with this property, which I don't have all of the hypotheses from the first slide up here, but we have a nice Riemann integrable function on a nice domain A with volume. The assumption here is that f is non-negative. And what we are about to prove is that if the integral of f over a is 0, but f is non-negative, that must mean that the set of points where f is positive is a set of measure 0. Let's give this set a name. I was about to say S, but we use that for rectangles. Let's call it E. We will show that the measure of E is 0. I really like this proof. I think it's clever. And since it's clever, as we work it out, you may come to this feeling of I wouldn't have figured that out on my own or something like that. So what we will do in just a moment is do just a little bit of scrap work and brainstorming so that you can see how from the brainstorming you might come to the sort of trick that we have in this proof. Let me give you an exercise, though, just to get you going on the brainstorming process without me. Let S be a nice rectangle enclosing A in the usual way. I won't write out the full thing right here. Imagine P is a partition of S. Into nice subrectangles, as we've been doing, partition of S. What I would like for you to pause and take a moment to do on your own is write down as much as you can for the lower sum of f with respect to this partition and the upper sum. So see how far you can take these notions. What's maybe the best or most conclusive statement that you can come up with? And if you really have a very good feeling for this, you might actually come up with a full proof. But again, I think that there's a little bit of a step from this brainstorming to what we will actually do in the proof itself. My apologies, a moment ago I realized I wrote S here instead of the partition P. So this is the lower sum of f with respect to the partition P and the upper sum of f with respect to the same partition P. We are just brainstorming here, so I'm going to use our standard notation without defining it at the same time. I hope you understand what I mean when I say S sub I in P. This is the family of subrectangles created by this partition. That's a finite collection of subrectangles. To compute the lower sum, we will multiply the infimum of f over the ith subrectangle times the volume of that subrectangle. Okay, so that's our standard approach to computing the lower sum of f with respect to this partition. Likewise, for the upper sum, it's the same collection of subrectangles, but this time we look at the supremum of f over the ith subrectangle times the volume of that subrectangle. This is where I would start trying to approach this proof if I didn't know how it was going to proceed. Let's start with the first line. What can we say about this lower sum? Well, for one thing, f is non-negative, so 0 is a global lower bound for this function. That means that each of these individual m sub I terms are going to be greater than or equal to 0. The volumes are greater than 0. So overall, this sum is greater than or equal to 0. On the other hand, if I considered a different partition, if I refined this partition, if I considered all possible partitions of S, and then I took the supremum, we would, if anything, go up in size to the lower integral of f over a. But we know that f is Riemann integrable. So this lower integral is really just the same thing as the integral of f over a, and we already know that by hypothesis to be 0. That's a 0. Reading left to right, we have 0 is less than or equal to this lower sum of f with respect to a random unspecified partition is less than or equal to 0. So of course, this middle term here is 0. So regardless of the partition, the lower sum of f is 0 with respect to that partition. So going back into this expression, we realize the only way we would get 0, considering that volumes of nicely defined subrectangles are non-zero, is if all of these were 0. Okay. So the infimum of this function over each subrectangle is 0. I don't know if that will be useful if I'm brainstorming, but it's a nice thing to recognize. Let's move on now to the upper sum of f with respect to this partition. We get this expression, and some of these might actually be 0. Some of them could be really small, but also some of them could be like a million. So I'm not really sure what I can say about capital M sub I at the moment, the supremum of f over any subrectangle created by any partition. And I can't really do like the same very conclusive statement here because this is greater than or equal to the upper integral of f, which of course, following the same thought process, is 0. Okay. Here's the thing, and I'm about to step away. I need to understand the measure of E. And the measure of E we want to prove is 0. If you have it handy, take a moment to revisit the definition of a measure 0 set. So what did we claim was possible for a measure 0 set? And if you read that definition, you'll recognize the importance of working with, in particular, this underline expression here in the summand, which is the sum of the volumes of these subrectangles. If I could say more here, I would be a lot happier or farther along this proof than I currently am. When I come back in just a moment, I'm going to focus mainly on this expression, kind of throwing away this lower sum, because while we made a very strong statement about it, having 0 in front of the terms we want to understand maybe isn't as useful as what we have here. Continuing our brainstorming session, let me say a little bit more about how upper sums behave, or rather what we can find amongst the collection of possible upper sums. Since the Riemann integral for this function over a is known to be 0, we know that the infimum of the set of all possible upper sums of f with respect to all partitions P of the enclosing rectangle S, this infimum is 0, because that's the upper integral of f, which is in fact the integral, which is 0. Okay, so the infimum of all possible upper sums is 0. Given any epsilon, there exists a partition, which we often denote P sub epsilon, so that the upper sum of f with respect to that partition is as small as you want it to be. Could be epsilon or some scaled version of epsilon. I'm just going to write epsilon now with the idea that we might adjust that. Okay, so looking at this, let me replace the left-hand side, scrapwork style with that sum that I erased from a moment ago. So this would be adding up over the subrectangles created by this special partition. Soups for the function times the volume of the relevant subrectangles. This expression would be less than epsilon, or some version of it. What we want to have is, given our epsilon, we want to find a family of subrectangles covering E so that the sum of their volumes is less than epsilon. This is measure zero. So hopefully you either remembered that or you paused and took a moment to revisit the definition of a measure zero set. But the idea was, for a set which has measure zero, you can find some kind of collection of rectangles. It actually doesn't even have to be a finite collection. It could be countably infinite, covering that set whose volumes sum to be as small as you like. So here I fixed epsilon and then I found my covering. Comparing this inequality to this one, it would be really nice if we could somehow divide out by this capital M sub I, but we can't. Maybe just think about that for a moment. What are the issues that arise if I start trying to isolate the sum of the volumes here? So experiment with this idea of can I bring this over somehow, find some kind of number which will neutralize all of these supremums? Just play around with this expression if you haven't done so yet. So let me show you one thing that fails. It's kind of weird because I'm going to write down something that doesn't work. But, I can't factor this in front of the summand because we're indexing here through with I. So you think well, could I maybe control this by some kind of fixed upper bound or lower bound? And here's what you might have come to. And that is, I'm just going to write this kind of in shorthand. If I sum up just the volumes, that's the expression I want to control. This is less than or equal to, if I put these volumes together with a coefficient which is greater than or equal to 1. How could you make such a coefficient? You could take all of these soups and divide them by the minimum of all of those soups. I'm sorry if you can't read this. Okay. So this collection of non-negative soups divided by their set minimum makes all of these coefficients here in front of the volume at least 1. So we've gone up in size. So that if I could then say that this is less than epsilon, so that I have my desired statement here, I would just need to show that this sum here is, say, less than epsilon times the minimum of the SIs. Okay, this is nonsense. It doesn't work out at all, right? So this is just brainstorming our way to a failure that we have to correct. You cannot choose a partition so that the upper sum is less than something which depends on the partition. So this right-hand bound that I really want to put here to kind of handle this underlining, this is not going to work. Given this number, go choose a partition so that the upper sum is less than this number, but this number is formed by the partition. It's circular. We have to have a fixed number over here. So usually it's epsilon, but sometimes it's epsilon over 2 or epsilon over 10 or something like that. But the idea is, for a fixed size limitation, you then go design your partition. We can't have our measurement depend on the partition. It creates interdependence, and that doesn't work out logically. Okay. However, this is still the spirit of the argument, but what we have to do is make sure that this minimum here is actually a fixed number that does not depend on the partition. That's all I will say right now. I'm going to jump right into the proof, but you will see how this comes into the proof. The trick that comes out in the proof traces back to this need that we identified, this need to somehow neutralize that coefficient so that we can get to the desired expression for measure zero. Here's the proof. I'm not going to show that this set E has measure 0 by looking at this set exactly as it's written. Instead, we are going to think of E as a countable union of measure 0 sets. We have to show those sets have measure 0, but it's a lot easier than working with E directly. So here's that family of sets for each natural number k, for each k in the set of natural numbers. Let's call it E sub k be a set consisting of all of the inputs from the domain A, whose value when plugged into this function f is greater than or equal to 1 over k. Not 0, a strictly positive lower bound. That's going to make things better. All right, we want to show that any such E sub k has measure 0, and that will be enough because E is the union of all of these E sub k. And we've already proved that any countable collection of measure 0 sets has measure 0. So since E is a countable union of sets which we will prove have measure 0, it suffices to show that each of these sets has measure 0. All right. Now returning back to the ideas of the scrap work, let's let epsilon be greater than 0. Since the Riemann integral of f over a is 0, there exists a partition which I will name P sub k because it's partnering up with this set. Of S enclosing A. I'm sorry, I'm kind of introducing these terms as if we've already seen them before, but thinking back to the scrapwork, S was a rectangle enclosing A. There exists a partition of it so that the upper sum of F with respect to that partition is less than, and here's where we had an issue before. It was how do we define that right-hand side in a way which is not circular? We want it to be less than epsilon over K. Okay, let's see what this gives us now. Thus, what I'm going to do is start with this and go down in size. That's not usually the direction that I do these kinds of arguments, but I think it will work out nicely here. So thus, epsilon over k, where k is a fixed number. I'm just thinking, we have k is all natural numbers indexing through here. So let me add here fix k in the set of natural numbers. Epsilon being 0, this is fine. Okay. All right. Fix a k. We're working with one specific k. We're going to show that E sub k has measure 0. So this number here is fixed. This number is greater than the sum over all of the subrectangles created by this special partition P sub k of the supremums of f with respect to each subrectangle times the corresponding volume for the ith subrectangle. What I'm going to do now is take this finite sum and break it into two collections of subrectangles. So this is equal to the sum over all of the subrectangles where mi is, let's say, less than 1 over k, plus the same type of sum, but for all of the sups which are greater than or equal to 1 over k. So I'm just rearranging these terms here into two groups. Each of these sups is greater than or equal to 0. The volumes are positive. So if I just got rid of this first collection, we would, if anything, go down in size to just this family. And this is actually very good. Okay. Now, we are going to take this in just a moment and use it to work out what the sum of the volumes is bounded above by. It's going to be epsilon, but we'll be able to pass through this collection to this bound epsilon over k in a way which is cleaning up all of the issues that we ran into a moment ago. let me have you digest this for a moment, then I will come back, erase all this, and we will wrap up the proof, given that we've established this bound. To give myself more room, I erased most of the proof. It's still there, though. Hopefully it's on your paper. I left this definition up there because we need to make an important observation at this point. Notice that this set is covered by the subrectangles created by the partition where the sup is at least 1 over k. Because if we're looking at inputs which get sent to values greater than or equal to 1 over k, the sup, of any rectangle enclosing some of this set is at least 1 over k. All right, so this is a subset of the union of SI such that MI is greater than or equal to 1 over k. I'm not sure I've notated this very clearly, but hopefully you understand. So any subrectangle in the partition which contains a point of E sub k is one where the sup will be greater than or equal to 1 over k, and we won't have any subrectangles whose sup is less than 1 over k contain any points satisfying this condition to be in E sub k. Okay, so we just need to show now that the volume of these subrectangles is less than epsilon. Thus, if I look at the rectangles here, so this special collection of subrectangles, and I add up their volume, that's the volume of the rectangles covering E sub k, it is less than or equal to, let me write k over k times the same volume. It's actually equal to because this is just a fancy version of the number 1. So one of these k's we can pull out. I'm just going to write sum here, same description for what we're summing over. 1 over k is less than or equal to m sub I. So this top k I'm pulling in front, the 1 over k I'm going to go up in size by replacing 1 over k with m sub I. Okay, this leading k stays out front, but now this expression is that expression that I ended with and erased a moment ago that we said was less than epsilon over k. So actually here, I'm going to go strictly up in size and say that this expression, that was that sub-collection from our sum that we kind of peeled off and identified was individually less than epsilon divided by k, and therefore we've reached the end. The volume of the subrectangles from our partition, specifically covering E sub k, adds up to a number less than our choice of epsilon. Therefore, maybe I'll say a little bit more. Thus, the measure of each of these E sub k's is 0. Their countable union gives us E. So the measure of E is also 0. Okay, that wraps up this proof. I think it's really neat. It's something, again, that you should try maybe later today or tomorrow when you're not looking specifically at your notes from this video. Remember this trick. If you can just remember that instead of saying, f is strictly positive, we put a floor on the values of f. That really gave us some useful abilities to create strict positive bounds that we could work with. See if you can reproduce it. We are done with this video where we had 3 properties, but actually we have more properties to look at in the next video. Thank you for your attention.